Hello students, today we are going to discuss the different formula to know the number of optical isomers of a compound. We know optical active isomers have a particular characteristics. They show different rotation towards the plane polarized light. It can rotate the light either clockwise or anti-clockwise. It depends upon the nature of optical active isomers. Different types of isomers are formed. Already we have discussed in the last videos that in organic chemistry, that videos number 11, that already we have discussed the types of optical active isomers, what are enantiomers, what are mesomers, what are diastereoisomers. Already we have discussed. You can refer these videos in the playlist of our channel, that is Chemistry Go. So today mainly we will discuss the different formula to know the number of optical isomers, how many optical active isomers, how many mesomers, that is optically inactive isomers, from the different formula. You see the groups, suppose one, I am writing one example, suppose this one, this is a compound. Here if you see, this is the chiral center, already know. This is your chiral center having different groups attached to this carbon atom. That's why it is called chiral center. And this chiral center, if you see the main chain, straight chain you can say, in this chain, this is the one terminal group, this is the another terminal groups. This terminal groups means end group. This is one methyl, this is your what? Carboxylic acid. So these two groups are different. If I write another examples for this one, HOH, here HOH, this is your COOH, this is your COH. You see, in this case, this is your one examples of chiral center, and this is also one example of chiral centers. Here the number of chiral centers are 2, but here this group, this is the one terminal group and this is also terminal group. Here these two terminal groups are same. Here these two groups are different. So these are the very important condition to derive the formula regarding the number of optical active isomers or mesomers. Here what happens, the rules that the formula is, when the terminal groups are different, for this like this, when the terminal groups are different, this is one terminal group, that is methyl group, and this is your acid group. When the terminal groups are different, then when different terminal groups are used, the formula is number of optically active isomer, OAI, number of optically active isomer is equal to 2 to the power n. This is called 2 to the power n. 2 to the power n means here n is the number of chiral center. So n indicates number of chiral centers and the terminal groups of the compound should be different. This is the condition. And the number of optical active isomer is equal to 2 to the power n. It is always same formula if the groups are different. Then racemic mixture, that optical active isomer will be produced as optical active isomers have two types of rotation, clockwise or anti-clockwise, dextrorotatory or levorotatory. So these two isomers are called, that is enantiomer. If these two isomer will be mixed with equivalent amount, the result is racemic mixture. So number of racemic mixture is produced always that half of the total number of optical active isomers. You have to remember this formula. total number of optically active isomers and racemic mixture. Racemic mixture is optically inactive. Already we have discussed that optically inactive means racemic mixture, that is plus and minus, that is called plus and minus. This mixture is called racemic mixture, and the number of racemic mixture produced will be half of the total number of optically active isomers obtained. Then when the terminal groups are same, this is very important. When the terminal groups are same, then the formula will be used that when n is even, when n will be even, if even number of chiral center is there, then optical active isomer is how much? 2 to the power n minus 1. 2 to the power n minus 1 is the number of optical active isomers when n will be even, and another condition is both are same, both terminal groups are same. Then number of optically inactive isomer is equal to 2 to the power n minus 2 by 2, to the power n minus 2 by 2. These are called also optically inactive isomers, or it is called also mesomers. Optical inactive isomers or mesomers, but optically active isomer is equal to 2 to the power n minus 1. It is 2 to the power n minus 2 by 2. Then total isomers. Total isomers means optically active isomers and optically inactive isomers. So result is 2 to the power n minus 1 plus 2 to the power n minus 2 by 2. You have to remember this formula. This is the total number of isomers produced, including optical active isomers and optically inactive isomers. Optically inactive isomers generally are called mesomers. This is very important thing. These are called mesomers. Then when n will be odd, this is the condition that already we discussed regarding even number, but when n will be odd, the formula will be total isomers. Total isomers formula will be 2 to the power n minus 1. 2 to the power n minus 1. Then how much optically inactive isomers? OIA means optically inactive isomers, that is 2 to the power n minus 1 by 2. Same formula, only 2 to the power n minus 1 by 2. This is the number of optically inactive isomers. Then how much optically active isomers? Because optical total isomer is equal to 2 to the power n minus 1 and optically inactive isomer is equal to 2 to the power n minus 1 by 2. So optically active isomer will be 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. So this is the formula of number of optically active isomers. So these are the different formula, important formula for the calculation of number of optical isomers. So let us discuss these examples. This is the, suppose this is the first examples. This, in this case, n is equal to 1. Here n is equal to 1 and the terminal groups are different. If terminal groups are different, then the number of optical active isomer will be always 2 to the power n. So OAI will be 2 to the power 1, that is 2. So result is 2. So 2 number of optical active isomers will be formed. One will be plus and another will be minus. That means this form. For this compound, one will be like this. You can use also mirror image like this. This is one example of isomers. Then mirror image will be used. Then OHCH3, then COH, then H. So these two. If it will be plus, then it will be minus. So this is only two optically active isomers will form if it has one chiral center. So this is the case, number of optically active isomers when groups are different. For examples, we can take, suppose glucose molecule. Glucose is CHO, then CHOH, then CHOH, then COHH, then CHOH, then CH2OH. You see how many chiral center is there? Number of chiral center. If you see, this is one chiral centers, this is one chiral centers, this is one chiral center, this is one chiral center. So how many here? N value will be 4. Here N is equal to 4. As N is equal to 4 and the terminal groups are different. Here terminal groups are different. At the different terminal groups and N is equal to 4, this is for glucose, this example for glucose. So optical active isomer will be 2 to the power n, that is 2 to the power 4, that is answer is 16. So glucose has 16 number of optically active isomers. If 16 number of optical isomers, how many racemic mixtures? So racemic mixture will be 16 by 2, that is 8. Number of racemic mixture always half of the total number of optically active isomers. Already we have discussed the formula. Racemic mixture is 2 to the power n by 2. When the groups are, terminal groups are different, this is the formula. Terminal groups are different means always it follow one common formula, that is 2 to the power n. Then another example, suppose if the groups are different, suppose you take this example, here COH, HOH, then HOH, then CH3. This is the case. Here what happens? The groups are different. Here terminal groups are different. Here terminal groups is, this is the case, terminal groups. Okay. If the terminal groups are different, then chiral center is 1. Here 1, 2. As 2, here n value is equal to 2. N value equal to 2. Then n value equal to 2. As the terminal groups are different, the formula is always 2 to the power n. So OAI, number of optical active isomer, will be 2 to the power 2, that is 4. And racemic mixture will be how much? Racemic mixture will be 2. Number of racemic mixture will be 2 and number of optical active isomer will be 4. So this is the case when the terminal groups are different. This is the first case and this is the one case, second case, this is the second case and this is the third case. When the terminal groups are different, we have to use the one formula, that is 2 to the power n. Now let us take one example when terminal groups are different. When the terminal groups are same, when the terminal groups are same, we have to use value of n. If n is even, if n will be even, then what will be the formula? If n is even, then optical active isomer will be 2 to the power n minus 1. For this case, n is equal to, that is how much? Here n is equal to 2. Are even. Even means how many optical active isomers? Optically active isomers OAI will be at the formula 2 to the power n minus 1, that is 2 to the power 2 minus 1, that is 2. To the power 2 minus 1, to the power n minus 1. Here number of chiral center is 2. So 2 to the power 2 minus means 2 to the power 1. 2 to the power 1 means that is 2. So 2 number of what? Optical active isomer is formed. how many optically inactive isomers? That is the formula OIA, number of optically inactive isomer will be 2 to the power how much? N minus 2 by 2, that is 2 to the power n minus 2. N minus 2 means n minus 2 by 2, which is equal to 2 to the power 2 minus 2 by 2, that is 1. So 1 mesomers will be formed. Mesomer is 1, that is optically inactive isomer is 1 and optically active isomer is 2. So total is how much? So 2 plus 1, that is 3. So in this case total isomer will be 3. So 2 for that is optical active isomer, that is 1 plus, another minus, and another will be plus and minus will be 1 plus 1 minus, and another is mesomers. What is the formula of this? Which will be the mesomers? Which will be the what? Enantiomers. You see the examples. In this case this formula shows it is a mesomers. This structure shows it is a mesomers formula, because here what happens, upper part is just equal to the lower part, so it has a plane of symmetry, so upper half is similar with lower half, that's why this structure indicates it is the mesomers. But if you write this in different way, if you write the structure in this way, that is COOH and HOH, then COH, H, then COH, this structure is just mirror image of this structure, just a reverse of this. C, this is the C, here OH, H and COH, then here H, OH, then COH, just opposite. This structure and these two structure just opposite. So, and this is the optical active isomers and this is the mesomers. Already we have discussed the type of optical active isomers, mesomers, diastereoisomers. So which will be diastereoisomers? Any optical active isomers when you take with any, just you compare with other isomers. Optical active isomers we'll discuss later. Optical active isomers but no mirror image, these are called what? Any two optical active isomers of any two, I select any two isomers, optical active isomers, but should not be mirror image, are called diastereoisomers. So these are the examples of different types of optical active isomers and the number of mesomers and number of optical active isomers using the formula. So if you take one examples, so in this case, suppose this is the case HOH and this is your COH, and this case this is your H and this is your Cl and this is your COH. In this case, my question, this is your homework for you. This is your homework. Here you will calculate that how many optical active isomer will form and what are the, which pair will be diastereoisomers and which pair will be enantiomers. Total optical active isomers and how many pairs will be diastereoisomer will be possible. In this case, here we can say this, that this is the chiral center, this is your chiral center, then how many optical active isomer will be formed, then how many will be diastereoisomers. So this, for this question you will send the answer in the comment box, then the answer will be discussed in the next class. Okay, So you have to remember the different formula used in the calculation of the optical active isomers. Similarly, if another question also we can discuss, that sucrose, this is the formula of glucose, this is the glucose, this is your glucose. If you take fructose also, this is the fructose formula, CH2OH and CO, then HOH, then HOH, then OH, this formula 1 2 3 4 5, then last one is CH2OH. This case, this is the structure of fructose. This is the structure of fructose, and fructose contains also 6 carbon, 1 2 3 4 5 6. But here how many chiral center is there? Chiral center is 1. This is your chiral center, and this is also chiral center, this is your chiral center. How many chiral center? 3 chiral center, but terminal groups are different. Here this is your terminal groups and this is your terminal groups. So 2 terminal, but this condition is satisfying the first condition, first rule, that when groups are different, these groups are different, and here number of chiral center is 3. So total number of optical active isomer will be 2 to the power 3, that is 8. So fructose has 8 optical active isomers, but glucose has 16 optical active isomers. And this fructose has how many raceme mixture? 4 raceme mixture, and glucose has that 8 raceme mixture. So these are the some important formula to know, to calculate the how many optical active isomers, how many measurements are possible. Measurements will be possible when the both terminal groups are same. But this is the case that homework I have given. Remember, it has no measurements because the groups are not same. Because you see here COH, HOH, here HCOH, Cl, as the terminal groups are different. If terminal group is acid, here terminal group is not acid. Here the one different group is Cl is there. So this structure, it has no measurements. In this type of structure, it has no measurements, only enantiomers and diastereoisomer is possible. And this case, only which measurements and optical active isomer is possible, no diastereoisomer is possible. So this is the very important cases. You have to practice and you have to calculate which case how many optical active isomer is possible, how many measurements are possible. Okay. Thank you all.